Well, good afternoon, everyone. Buenas tardes, and welcome. We are delighted that you have joined us for this very special lecture today. Before we get started, I'd like to thank a couple of people who played a key role in this presentation. First, Dr. Vivian Inceda, Chair of the Physics Department, for spearheading the effort to bring this very special speaker to the UTEP campus. Thank you, Vivian. Please stand up so we can thank the Dean of the College of Science, Dr. Animo Robert Sosa, for co-sponsoring this evening's lecture with us. We're truly honored today to have with us Dr. Douglas Osheroff, J.G. Jackson, and C.J. Wood, Professor of Physics, and Gerhard Casper, University Fellow in Undergraduate Education at Stanford University, and co-recipient in 1996 of the Nobel Prize in Physics. Dr. Osheroff and his colleagues David Lee and Robert Richardson were awarded the 1996 Nobel Prize for their discovery of superfluidity in helium-3. Because our audience today is not exclusively populated by physicists, I'm relieved to be able to simply note that this breakthrough in low-temperature physics made in 1971 has proven to be a critical factor in later, indeed now current, experimentation in quantum physics and cosmic strings. Always inquisitive and fascinated by natural science from a young age, Douglas Osheroff managed to survive the occasional basement laboratory fire and minor explosion, graduating from Caltech with a bachelor's degree in 1967. He joined the Laboratory of Solid-State Physics at Cornell University for his graduate work, and it was there that he, Lee, and Richardson conducted the investigation that produced a discovery that changed the way scientists approach the study of nuclear physics. And 25 years later, he was recognized with the Nobel Prize. Dr. Osheroff earned his PhD at Cornell in 1973. From there, he moved to Bell Laboratories and continued to conduct solid-state and low-temperature research until 1987. He then joined the faculty of Stanford University, where he remains a professor of physics and applied physics. His current research focuses on studies of quantum fluids and solids and gases at ultra-low temperatures. In addition to the Nobel Prize, Dr. Osheroff is a recipient of the Simon Memorial Prize and the Oliver Buckley Prize, was named a MacArthur Prize Fellow, and was awarded Stanford's Walter G. Gores Award for teaching. He's a Fellow of the American Physical Society and the American Academy of Arts and Sciences, and he's a member of the National Academy of Sciences. Please join me in extending a very warm UTEP welcome to our very distinguished guest today, Douglas Osheroff.
Well, it's very much my pleasure to be here today. I heard that UTEP is a beautiful campus, and it certainly is, and I've had a great deal of pleasure talking with many of your undergraduate students today. So this is a public lecture, and I think it's a public lecture. And so hopefully there won't be an awful lot of physics in this, but it's a talk about how physics is done, and I hope you will enjoy it. Is it possible to kill some of these lights and get a little bit, I don't know if that's, that way you can all sleep a little bit more easily. That's much better. There we go. So this, by the way, is one of my photographs. You will see a bunch of them during this talk. This is a single wave off the coast of Bali. And one of the few real advantages in getting a Nobel Prize is you get to do a lot of travel. So I visited 40 countries, and I think almost all of those were since getting the Nobel Prize. So the title of this talk is How Advances in Science Are Made, and it is really a talk about what strategies allow you to make discoveries, and by looking at a number of discoveries and seeing how they have been done. So let's start out and see how things go. So there are a few messages in here, and this is the first. Those discoveries that most change the way we think about nature cannot be anticipated. How then are such discoveries made, and are there research strategies that can substantially change one's chances of making such a discovery? And the background is the Grand Canyon at sunset on December 28th, 2004. I can't remember it. Okay, so I will illustrate this with a linked chain of discoveries and inventions, starting, I always like to look at the screen, this person here, who is one of my great heroes, and I dare say, without his contributions, I would not be here tonight. You all know who this is. This is Heikki Karelionis, who first liquefied helium in 1908. It's an interesting story. Karelionis and Dewar were in a competition to see who could first liquefy the lightest and most inert of the atmospheric gases. And it looked like Dewar had won when he succeeded in liquefying hydrogen in, I think it's around 1895. Maybe it was 1902 anyway, but already evidence for the existence of helium had been obtained from spectral lines coming from the sun, and within a few years Karelionis was able to get enough helium to attempt to liquefy. I think it was actually only what you might put in a medium-sized party balloon. But he succeeded in doing that in 1908. And then he did exactly what Dewar had done with hydrogen. He pumped on the vapor above the liquid, and in the process the liquid would cool due to the evaporation. And the idea was to find out at what temperature helium solidified. Well, he continued on this experiment for 2 solid years, ultimately reaching a temperature of 1.04 degrees above absolute zero. But the helium never solidified. Now, I can tell you that I personally have cooled liquid helium-3 to a temperature of 1/10,000th of a degree above absolute zero, and it still remains very happily in the fluid state. That has to do with quantum mechanics, in particular the Heisenberg uncertainty principle, which was, quantum mechanics was just being developed at this time, so there's no way that Karelionis could have possibly understood why he was unsuccessful in solidifying helium-4. However, what was I going to say now? He liquefied helium, and then after he spent 2 solid years trying to solidify helium-4 without success. Now you can do it if you apply a pressure of 25 bars, but that hadn't occurred to Karelionis. After 2 years of trying to solidify helium-4, he gave up on that and decided to look for some other great question of the day that he could answer with this unique refrigeration device that he developed. And so people were arguing about what would happen to the conductivity of a very pure metal if it were cooled arbitrarily close to absolute zero. And so one school of thought was that if it was a very pure metal, as you eliminated the lattice vibrations associated with the temperature, the heat, that in the conduction electrons would travel longer and longer distances before scattering. So the electrical resistance would very slowly drop to zero. The other school of thought suggested that at some point the conduction electrons, which are free to roam around the interior of the metal, are not associated with any particular atom, would recondense on the atoms from which they had come, and all electrical conductivity would cease. So he obtained a very pure sample of mercury and gave it to his student, Gilles Holst. I put Gilles Holst's name up here. Camerlionis was not of the habit of putting his graduate students' names on his research papers. I'm so happy that Dave Lee didn't have the same attitude. So here you can see, these are the data points that Gilles Holst found. This is resistance 0 to 2,000ths of an ohm, and the temperature goes from 4 to 4.5 degrees Kelvin. And so you can see, in fact, that the resistance was slowly dropping, but then at a temperature of about 4.2 degrees, there was a nearly discontinuous drop in the electrical resistance to a value which was less than 10 to the minus 5 ohms, which was the resolution of their instrument for measuring resistivity. And so when Camerlionis first saw this data, he was sure that an electrical lead had fallen off of the sample, and I dare say I probably would have said the same thing. But of course, this is physics, and so you expect these results to be easily reproduced, and they were. This, of course, was the first observation of superconductivity. And superconductivity, I dare say, has been studied in many places around the world ever since that time. Superconductivity is, of course, one of the most fascinating features of condensed matter physics. So let's look at the research strategies that allowed this discovery to be made. By the way, I should say that in 1913, Camerlionis was awarded the Nobel Prize for Physics for having cooled, having liquefied helium and having measured the properties of matter at these very low temperatures. I suppose that alluded to the discovery of superconductivity, but it wasn't specifically for that effect. So here we see, number one, use the best instrumentation available, and he had a unique device that allowed him to reach temperatures far lower than those that anyone else could obtain in the world at that time. Don't reinvent, borrow the technologies you can. Dewar had invented the Dewar flask, or thermos jug as we call it today, to allow him to liquefy hydrogen, and Camerlionis was very happy to borrow that technology, or at least make similar devices inspired by Dewar. And now look into an unexplored region of the, I should say, physical landscape. So if you want to make a discovery, it really helps, but it's not absolutely necessary, to look at some aspect of nature in a new or different realm. And I dare say that I didn't tell you this, but when Camerlionis had liquefied helium, he had pumped it on the vapor above the helium and cooled it down to a temperature of 1.4 Kelvin. And he recorded in his lab book that it appeared that the helium stopped boiling at a temperature of roughly 2 Kelvin. Well, if he had looked at that further, he would have found that in fact, at that temperature, 2.17 Kelvin, liquid helium becomes a superfluid. However, he did not do that. So failure, I dare say, might be an invitation to try something new. Oh, wait a minute, I'm getting all these things confused now. I've given this talk probably 100 times. so look into an unexplored region of the landscape, and failure might be an invitation to try something new. So the idea there is that after failing to solidify helium, he tried something else. He looked at the conductivity of metals, and that's when he discovered superconductivity. And finally, and this is the last one, be aware of subtle, unexplained behavior. Don't dismiss it. And that refers to the fact that something strange seemed to be happening in the liquid helium itself. If he in fact had looked into that further, he would have found what this gentleman found. This is Peter Kapitsa, who in the bleak winter of 1937 in Moscow measured the viscosity of liquid helium below its superfluid transition temperature and found that viscosity to be less than 1/1000th of a poise. And for that, Peter Kapitsa shared the Nobel Prize in 1978 with two very unlikely colleagues, in the sense that that the other people's work had nothing to do with helium in any way, but perhaps maybe to do with low temperatures. And those gentlemen are people that I know. Actually, before he died, I had met Peter Kapitsa before. That's a very interesting man, and had lots of wonderful stories. Those gentlemen were Honore Penzias, who was my boss's boss at AT&T Bell Laboratories, and Robert Wilson. And Penzias and Wilson were interested in making the first absolute measurements of cosmic radio noise coming from extraterrestrial sources. Now, it turns out that AT&T at this time had been doing experiments on satellite telecommunications using a very special microwave receiver that they had built, which is shown here. Now this, of course, looks like a very high-tech piece of equipment. This is a horn antenna, which has the advantage that it doesn't intercept radio signals coming from the ground, only from where it's pointed. But the real key to this is inside this little shed where there was a amplifier of these microwave signals that in fact they characterized the noise that an amplifier adds to the signal as the noise temperature. And that noise temperature was the lowest of any device. In fact, the amplifier itself was cooled to a temperature of 4.2 Kelvin. It was, in fact, a maser amplifier. And maser, of course, was invented earlier by this gentleman here. This is Charles Towns. Last summer, I attended Charles Towns' 95th birthday, and he's still very active, a remarkable person. So this is at Columbia University, Charles Towns, and his graduate student, Jim Gordon, created the first maser, microwave amplification by stimulated emission of radiation. And using this device here, this is actually not the first maser, but the second maser, using ammonia atoms, which are sorted, so you only would pass through the atoms which are in an excited state. But this sort of device wouldn't have been adequate for what Penzias and Wilson needed. However, Nicholas Bloomberg, a professor at Harvard University, refined the maser technique to make it useful for amplifying microwave signals by doping a ruby rod and then cooling it to a temperature of 4.2 Kelvin. Now you might ask why AT&T, a communications company, would be interested in looking at noise coming from outer space. And I'm quite sure that it really has to do with this person here. This is Karl Jansky, who was in 1933 an engineer working for AT&T in what became Bell Laboratories. And AT&T was interested in transmitting telephone conversations using radio waves, but they found that there was excess noise that they couldn't get rid of. So they asked Karl Jansky to find out what the origins of that noise were. And so this is in fact a rate directional antenna that only looks at signals coming directly downward. And Jansky would look at the radio noise being received by that antenna as a function of the time of day. And he looked at this for, I guess, several months. And what he found was that there was always a peak in the radio noise, but the peak varied from day to day. So its period wasn't 24 hours, it was 24 hours minus 4 minutes. So anyone that knows anything about astrophysics knows that that's sidereal time, suggesting in fact that the clock that was governing this process was extraterrestrial. It had nothing to do with the rotation of the Earth. And so in fact, Jansky talked to his boss at AT&T and said he wanted to find out where this noise came from. But AT&T said, well, if it's coming from outer space, there's nothing we can do about it. So they reassigned him to another project. And I suspect that the management at Bell Laboratories was very different when Penzias and Wilson did their work many years later. This is 1933, and Penzias and Wilson did their work in 1978. So Jansky didn't actually find out where the noise was coming from. That actually, a fellow named Reber was the person that actually did that. He was a ham radio operator, believe it or not. But Jansky won in the end because, in fact, the unit of radio noise now is called a Jansky. So Jansky is 10 to the minus 26 watts meter squared per watts meter squared hertz. And let's go on now. This is the actual data that Penzias and Wilson got. That was an aside. So they were looking at this radio noise. They pointed the antenna at a point in the sky known to contain no radio sources. This is 1978. We know those things. And so here they're looking at the noise coming in on the antenna, and these are the directions it's pointing. And then they had a microwave switch that allowed them to compare that signal to the noise being radiated by a black body at a temperature of 4.2 Kelvin. This is that cold load is what they call it. Then they do some calibrations. What they concluded was there was excess noise that they couldn't understand at the level of about 3.3 Kelvin. That's this number down here. And so they went back and looked at their antenna, and they actually went inside the antenna, and they found that the pigeons were roosting inside the antenna. So they knocked down the pigeons' nests and mopped up the pigeon droppings, and I think there were a few copper plates that had to be resoldered in place because of the corrosion. But nothing that they could do would get rid of this excess noise that they had seen. And in fact, they found that wherever they pointed the antenna, if there was a place where there was known to be no radio noise signals, sources, in fact, they would see this noise. So one day, Arnold Penzias was talking with a Professor Burke up at MIT about this very strange noise that they had. And Burke suggested that Penzias should talk to Robert Dicke at Princeton. Now it turns out Robert Dicke actually there had been predictions that there would be radio noise left over from the Big Bang, actually, and that Dicke was actually looking for this radiation. But he was using a receiver, microwave receiver, with a conventional tube amplifier, and the integrated noise temperature of his device was 2,000 Kelvin, whereas the integrated noise temperature of Penzias and Wilson's device was 19 Kelvin. So I think you can see here that having the best technology really helps. So now we, of course, know the temperature of that radiation very well. This is thanks to the Kobe satellite. I think it'll help if I put my glasses on, because then I can actually see what's here. So it's 2.725 Kelvin with an uncertainty of 1,000th of a Kelvin, and it has this very specific shape, which is characteristic of the cosmic microwave background radiation. So let's look at the strategies that allowed this discovery to be made. First, use the best technology available. I dare say that Penzias and Wilson essentially borrowed that technology, most of it from AT&T, but they made this one modification in that device. They added this microwave switch, which allowed them to compare the noise signals being received by their antenna to the noise radiated by a black body at a temperature of 4.2 Kelvin. That really allowed them to understand the nature of what was going on there. And without it, I suspect they probably wouldn't have made this. So don't reinvent the wheel, borrow if one can. And that's referring to the receiver. Look into a region of parameter space that is unexplored. Now, a lot of people had looked at radio waves coming from extraterrestrial sources, but no one had looked at absolute measurements. And so when you start looking at absolute measurements, you can see very small things, and that's how they were able to find this. And probably for experimentalists, I would say this is the most important of these strategies. Understand what your instrumentation is measuring. So often today, people will find very small signals that they don't understand, that they will ascribe it to their apparatus, and then they will subtract that from what they record. And of course, if they do that, they're going to miss something. So I think understanding your equipment is extremely important. There are so many stories. I don't have time to tell all of them of people that have an apparatus and they see something wonderful and only to find in the end that it isn't there. That's exactly the opposite, of course. But there are people that have unfortunately seen something and not known where it was coming from until they tore apart their apparatus and put it back together again. So it's interesting that the Kobe satellite actually saw this and got this wonderful spectrum, but it turns out that the cosmic microwave background radiation is not uniform over the sky. If you look at what the Kobe satellite saw, first you see that in the direction that the Earth is headed, that radiation is a little bit hotter because it's Doppler shifted to higher frequencies, and the other direction is a little bit colder. Now, as a physicist, of course, I find it very disconcerting that one thinks red things are hot and blue things are cold, because we all know that blue things are shorter wavelengths and higher energies than red things. But anyway, so that's the case. So you can get rid of this very easily. And then what you find is, in fact, it's still not uniform. This is the plane of the Milky Way galaxy, and that's where all of this radiation that Reber found is coming from. And you can get rid of that, and then you're still left with all these fluctuations. This clearly looks like noise on noise, but in fact, it's reproducible. That's the important thing. And in fact, now we understand that these fluctuations are due fluctuations in the density of the universe at the time that matter became neutral. At that point, matter and radiation separated from one another. That was about 400,000 years after the Big Bang. So this is, in fact, the best means we have of looking back at the early universe right now is this cosmic microwave background radiation. So I dare say that this keeps going on, and this is John Mather and George Smoot. They were the architects of the Kobe satellite, and they got their own Nobel Prize just 2006, so it wasn't really very long ago. But in fact, this whole business of probing the early universe continues. This is something called WMAP. The W stands for Wilkinson. Now, David Wilkinson was one of Robert Dickey's graduate students back at Princeton when Robert Dickey was trying to measure the cosmic microwave background radiation. He was one of the people that was an architect of this MAP, microwave anisotropy probe satellite, but unfortunately he died before the satellite got up into orbit. This unfortunately happens fairly often with NASA satellites. The time you have to wait for your satellite to launch can be quite long. Anyway, I knew David Wilkinson. He was a really nice person. So now the background, by the way, is a very small portion of the Iguazu Falls at the border between Argentina and Brazil. And I will put my glasses on so I can read this. The process of advancing science often leads to inventions and technologies that directly benefit mankind. However, it is impossible to know from where an advance will come that might solve a particular problem facing mankind. Consider, for example, nuclear magnetic resonance. Now, I must say that I use nuclear magnetic resonance in my own research all the time. I'm going to take a sip of water just a minute. I'm sorry, I can't share. Okay, NMR was actually invented by these two gentlemen. This is Felix Bloch, Stanford University, and Ed Purcell at Harvard University. Now, Felix was a bit of a curmudgeon, and I'll tell you why that was important in a minute. These two invented NMR in 1946, and in just 6 years, they shared the Nobel Prize for this. And I know exactly what happens when you get a Nobel Prize. the press come up and they say, explain NMR. And you know, it's complicated. These people don't know any science. So after a while, they give up and they're ace in the hole. They play their ace in the hole, which is, what do you think NMR is going to be good for? And so they did that with me for helium-3, which is not good for anything. You can ask me how I ended up getting the Nobel Prize. But anyway, so Felix Bloch, when asked that question, is reputed to have said, damn little. It was in keeping with his personality. And Ed Purcell, who's a very thoughtful person, suggested that perhaps one could use NMR to calibrate magnetic fields. So these are the visionaries that invented NMR. Now let's look and see what NMR has actually been good for. Well, people found that if they could create they tried hard to create very uniform magnetic fields, and then if they did NMR on hydrogen atoms, protons, essentially, in organic molecules in aqueous solution, that they would find you get spin triplets and quadruplets, where you get 3 and 4 resonances where you expected to have only 1. And it didn't take very long for them to realize that these were due to chemical and spin shifts coming from the fact that these atoms are relatively close to one another, so they feel the magnetic field from the other atoms. Oh, went the wrong direction. Okay, so the next thing was really, this is from Richard Ernst. Mostly Richard Ernst was actually, he's Swiss, but he was working for Varian Associates in Palo Alto, and he had a suggestion that would really make NMR a lot more useful. He said, rather than slowly sweeping the magnetic field and recording all these signals that you get out, he said, why don't you just apply a very sharp pulse of rotating magnetic field, and that would then tip all of the nuclear spins over, and they would all precess, and then you record that signal and take a Fourier transform, and that would basically give you the distribution of frequencies of all of the spins in your sample. This is a Fourier transform NMR. So that idea completely revolutionized NMR, pulsed NMR, and so then Richard Ernst and Kurt Wuttrich invented all sorts of very complicated sequences to allow them to measure bond lengths in fairly complicated molecules. And so in 1991, Richard Ernst was awarded the Nobel Prize. Now the first prize to Purcell and Bloch was in physics. This one was in chemistry in 1991. And it's interesting because it seems like everyone that gets a Nobel Prize smiles. I don't know why that's the case. So Kurt Wuttrich wasn't smiling, though. I asked him, I said, how did you feel when it was announced that your collaborator, Richard Ernst, had won the Nobel Prize and you didn't share it? He said, I said, you must have felt disappointed. He said, no, I didn't feel disappointed. I felt mad. So as a man possessed, Kurt Wuttrich then labored on mightily until he was able to actually determine the three-dimensional conformation of things as complicated as simple proteins. This is the bovine pancreatic trypsin inhibitor. The big issue was that if you crystallize these proteins, would they have the same structure, three-dimensional structure, as they would have in an aqueous solution? It wasn't clear if that was the case. The answer was yes. And so then in 2002, Kurt Wuttrich got his own Nobel Prize. And if you look very carefully, you'll see that he's actually smiling too. Okay, but we're not done, because during this whole period, and starting back, I suppose, around 1971, people began to realize that if they applied a magnetic field gradient across their sample, in fact, they could obtain information about the three-dimensional distribution of the nuclei in their sample. This, of course, sample happens to be this is a healthy human knee. Now, I would say that my right knee, I used to say, was unhealthy, and you could see it very easily with magnetic resonance imaging, MRI. However, it's been replaced. I have a titanium knee now. Works very well. Thank you. So for their work, now I think there were a lot of people that worked in the development of MRI, but I think two people who really stood out. One was Paul Lauterbur, shown here, and Peter Mansfield. And these people shared the Nobel Prize, and this time NMR for physiology or medicine. So the Nobel Prizes in physics, one in physics, two in chemistry, and one in physiology or medicine. It's quite a remarkable thing. Now, if you go back and think about what the visionaries that invented NMR felt it was going to be good for, in fact, they obviously hadn't anticipated any of these things. So I think we're not done, though. I think it's very likely, or at least I hope it's very likely, that in fact NMR will win another Nobel Prize for another serendipitous discovery. At Bell Laboratories, there were two people in the biophysics department. David Tank was the head of that department, and Seiji Ogawa, who were looking at rats' brains. I think these, I believe, are human brains, not rats' brains. And what they found was there would be places in the brain that would light up because they were using a particular pulse sequence that was very sensitive to the rate at which the nuclei relaxed along the magnetic field. And this allows you to see those places in the brain that are processing information. It's due to the fact that as the brain does its work, it changes the oxygenation state of hemoglobin. Hemoglobin provides the oxygen for every process in the body. And so my hope is ultimately, you cannot, of course, know what the person is thinking, but you can certainly see those parts of the brain that are doing the work. And so my hope is that ultimately fMRI will prove to be sufficiently important that NMR will win a 5th Nobel Prize. So now, after I take another sip of water, I of course don't know an awful lot about any of the discoveries and inventions that I've just talked about, but I will talk about my discovery, which is the discovery of superfluidity helium-3, and you get, I think, maybe a better feeling for how these discoveries occur. Well, first of all, let me say that I grew up in Aberdeen, Washington, and Kurt Cobain was my high school classmate. Oh, no, sorry. Don Cobain, his father, was my high school classmate. I was just testing you. Anyway, so this is me. And the reason I put this picture up is not because of me, but rather because of William Hawke, who was my chemistry teacher. He actually had a profound impact on the way I think about research. And he had been a graduate student at Stanford University, was married with kids, eventually ran out of money and dropped out, became a high school teacher. This is a very sad story, but it happens all too often. And so he became a teacher in Aberdeen, Washington. I was fortunate enough to be one of his students. One day he came into class and he had a milk carton. Something was inside the milk carton. He shook it. You could hear there was something. He says, research is like trying to find out what's inside the milk carton. You can do a series of experiments, and every time you do an experiment, you're asking nature a question. Nature has to answer your question, but nature's answers aren't what's inside the milk carton, it's something about what's inside the milk carton. So he said, for instance, if we rotate the milk carton about its long axis, and what's inside rushes from corner to corner, we know that that thing has to have cylindrical symmetry. And so this, I suppose I processed this idea in my head for quite a long time. And what I say is, okay, the idea of research is to ask nature a bunch of questions and trick her into giving up one of her secrets. And to this day, it is a wonderful game that I play with nature. And it's just, I think it is absolutely right. And unfortunately, William Hawke Well, he left Aberdeen and started teaching in Los Angeles, but then William Hawk was someone who absolutely needed respect from his students, and unfortunately he didn't get that respect. So he stopped teaching and started working for the Food and Drug Administration. And I dare say, periodically I would call him up and we'd talk on the phone, almost even after he had a stroke. It was very difficult. He would mainly listen after that point, but he had a profound impact on me. And I think this happens, and when it happens, I think it's really important that students make it clear to the person that had that impact how fortunate you were and how thankful you are. So now, okay, we're done with high school. When is he going to be done with this talk? We're off to Caltech. I was an undergraduate. I dare say that my brother was an undergraduate student at Stanford, and at first I thought I would go to Stanford, but then I said, if I go to Stanford, my academic record will be compared to my overachieving older brother for 4 more years. And so I went to Caltech, which was, I think, a very difficult solution to that problem. However, this was the time when Richard Feynman was teaching his famous 2-year sequence to all of the undergraduates. And for me, it was absolutely fascinating, and I just loved it. I dare say, though, that my freshman class started out at 192, and only 120 returned for their sophomore year. And I suspect that Richard Feynman had something to do with that. Because the people that were left in your sophomore year, the fall of your sophomore year, if you wanted to declare a major, you had to meet with a representative of that major. And I dare say that 2/3 of the remaining members of my freshman class were at that meeting. And so this fellow, Robbie Vogt, looks around and says, that which is to say 80 out of the 120. And he says, surely you're not all going into physics. It's much too hard. If you're not near the top of your class, and I was doing quite well in physics, but not so well in math. It was a very strange thing that Caltech started you with integral calculus, assuming that everyone had had differential calculus. But in fact, I went home that December, and I went to the principal and I said, I was crucified because of the fact that you don't offer calculus. And he says, well, Douglas, we wouldn't want you to specialize too soon. Anyway, so Feynman for me was he was, of course, a character who was larger than life. And I can tell Feynman stories, but they were not my stories, they were other people's stories, except many years later, when I was at Bell Laboratories and Caltech was trying to hire me, I went in to pay my regards to Feynman because he was, actually everyone knew he was dying of stomach cancer, and telling him how important his teaching was to me. And we ended up talking for a while, and I invited him to visit Bell Laboratories. And I was the host of that visit. It was quite fascinating. But that's after dinner conversation, not the middle of this talk. So anyway, as an undergraduate at Caltech, I got involved in research. There was a group headed by Gary Neugebauer and Bob Layton who were really had developed infrared, very sensitive infrared detectors, which allowed them to really look at the cosmos for things, particularly that you couldn't see in the visible. So we were, actually it was a survey telescope that was cataloging all of the bright and particularly the variable infrared sources. And of course all of this stuff is invisible, but I couldn't show you a picture in the infrared, you wouldn't see it. So I worked during the summer, and that was when not me, but two members of the group discovered the center of the Milky Way galaxy in the infrared. You can't see it in the visible because at short wavelengths the scattering is too strong. There's too much dust between us and the center of the Milky Way galaxy. So at that point everything stopped, and all of the graduate students and undergraduate students started making ever more refined infrared cameras, and these things were first put on. It was a 24-inch telescope, and then the 60-inch telescope, then the Hooker telescope, which was 100-inch, ultimately the Hale telescope at Palomar, the 200-inch telescope. And being involved, that was really exciting. So when I was applying for graduate study in the fall of my senior year, I was looking for schools that had good astrophysics programs. And I dare say that I actually was accepted to every school I applied, which goes to show how lucky I am. Eventually I had an epiphany when I realized that astrophysicists can't do experiments. You cannot change the temperature of a star and see what happens. And this suggestion from William Hawke was so strong, and it had grown for so long, that I ultimately decided not to go into astrophysics. I wanted to go into condensed matter physics, where the experiments typically were done in 1 or 2 months, and so you could do several per year, off to Cornell in condensed matter physics. So this is, in fact, my first year of graduate study. There were 2 talks given at Cornell that really strongly influenced what I did. One was a talk about the helium-3, helium-4 dilution refrigerator. It's a new refrigeration technology. This is the one that I built mostly during my first year of graduate study. This thing would actually cool matter down to 15 thousandths of a degree above absolute zero. And so this was, it was just wonderful to be able to go in there. But there was another technology, and the other technology I think had an even bigger impact on me. And that technology, interestingly enough, had been suggested by a Russian theorist named Isaac Pomeranchuk. Pomeranchuk was a member of the Landau School, which meant he was very broad. And in 1948, Ed Hamel at Los Alamos National Laboratory liquefied helium-3. So the helium-3 that he had came from the tritium source that he was supposed to be keeping clean. He was responsible for keeping the tritium clean while Los Alamos attempted to build a hydrogen bomb. So he saved the helium-3, and then ultimately he published his measurements of the helium-3 vapor pressure as a function of temperature. And so that actually was published in early 1949. Very soon after that, the Russians started doing their own work. Ed Hamel actually said how big his sample was, but the Russians never did. And I interviewed him on the phone when he was in his 80s, and he said he reckoned that was the first serious security leak at Los Alamos, because by saying how much helium-3 he had, he was telling the Russians something about how much tritium Los Alamos had and how long they had it, because it takes 12.4 years as the half-life for helium-3, for the decay of tritium, rather, into helium-3. So Pomeranchuk, at that time, started thinking about the properties of helium-3. The atoms have a net spin of 1/2, which means that they're Fermi particles. And so he realized that at low temperatures, the entropy of liquid helium-3 should drop linearly towards zero. But in the solid, he argued that the spins would be separated from one another. The atoms are separated, and the magnetic interaction between two helium-3 atoms in the solid would have a characteristic temperature of only a few millionths of a degree. Actually, probably maybe even smaller than that. So he figured that in the solid, the entropy would be essentially constant. There are 2 states available. The spin could point up or point down. So per mole, that would give you an entropy of R log 2. And that's this line here. And you can see that the liquid and solid entropies would cross at a temperature which was estimated to be about 3/10 of a degree. This is kind of remarkable if you think about the fact that Pomeranchuk was mostly interested in high temperature plasmas. So in fact, if you work out then, this is a very unusual situation, because you normally think that solid is more highly ordered than liquid and have a lower entropy. And it's just the opposite of that. And so the latent heat then ends up being negative, because the entropy of the liquid is less than the entropy of the solid. This is the phase diagram of helium-3. This is the liquid down here, this is the solid up here, and you get a negative slope because from the Clausius-Clapeyron equation, again, this term in the top is going to be negative. And so all of this was known by the time I was a graduate student, but in fact, no one had actually built, one person had built a Pomerantsev cell. And that was one of Peter Kapitza's students, the Kapitza that I showed you that got the Nobel Prize, shared the Nobel Prize with Penzias and Wilson. He had a student named Onufriev who built the Pomerantsev cell, and he started at about 100 milledegrees, and he cooled along this phase boundary and got off the melting curve at about 20 millikelvin. Now, my dilution refrigerator would get colder than that, but this was a proof of principle that this technology worked, and Dave Lee had read his paper, and so Dave Lee had suggested I should develop a Pomerantsev cell. So this is my Pomerantsev cell. Liquid helium-3 was down here. Now this should look golden. It does up here, but it doesn't up there. It's golden because helium-3 is very expensive, and it's become much more expensive recently because the Department of Homeland Security wants all of the helium-3 to use to detect neutrons, so that if a ship is coming into a port with an atomic bomb on board, you can detect it because the neutrons go right through the ship. So anyway, this is helium-3 at about a mole of helium-3, and the idea is you compress it by pushing a metal bellows to decrease the volume of this, and then you can start forming some solid. And the force is generated by adding helium-4, superfluid helium-4, under pressure to this top part. And then I measured the pressure using a very elegant capacitive pressure transducer invented at the University of Florida. And I measured the temperature by looking at the polarization of platinum-195 nuclei in a magnetic field. It's just basically a Boltzmann distribution. And so at the end of this, I think probably the most important event of my graduate career occurred, and that is that I got married at the end of my third year of graduate study. Liu Shijung, who I had met the day that I arrived at Cornell University. I went into the women's graduate cafeteria. It was the only cafeteria open on campus. This is still in August. And I saw this cute little Chinese girl sitting by herself eating. And I quickly got some food and sat across the table from her and invited her out to dinner. That wasn't such a good thing because I took her to a steakhouse. She'd never had a large chunk of meat before in her life. Anyway, so we now have been married for 40 years. And the reason this is important was that she was, at this point, she'd taken a postdoc in biochemistry. And she was a professional woman. She's been doing research all her life. But this basically meant that she was busy while I was busy. And so, by contrast, the student that I apprenticed under at Cornell earlier on was married with 2 children. And his wife couldn't wait to get out of fertility flats. That was what they called married graduate student housing. And so he actually wrote his PhD thesis and left blank spaces for the numbers. That ensured that he would not discover superfluidity in helium-3. I've actually had interesting conversations with him about that. So I think, you know, it's really interesting, but I think your partner in marriage, even if that person doesn't participate in your research, can in fact play a very important positive or negative role in how that research goes. So then going into my last year of graduate study, I asked Dave Lee what I should do for my PhD thesis because my wife was now in the second year of a 2-year postdoc in biochemistry. And he said, well, it's very simple. Why don't you measure some property of solid helium-3 through the nuclear spin ordering transition? Well, everyone thought that was actually at 2 milledegrees, but it's really the temperature of 9/10,000ths of a degree. No one had ever measured it, and no one had a thermometer that would stay in equilibrium with the helium-3 to these low temperatures. So I really didn't know what to do. And then toward the end of the summer, John Wheatley, who was a very famous, much more famous physicist than anyone at Cornell at that time, had published a paper where he looked at what happened as you at the melting pressure of helium-3 as you apply large magnetic fields, because of the fact that each helium-3 nucleus has a magnetic moment associated with it. The theory had suggested that there should be a very small downturn, a shift in the melting pressure at constant temperature, or the shift in the melting temperature, constant pressure. Here it's melting temperature, constant pressure. And my data, in fact, that I obtained were in fact consistent with that, but there was a lot of scatter in the data. The data that John Wheatley got and that excited everyone is shown near those, huge effect, much larger than theory had suggested. And of course what I found was that those measurements were wrong, because Wheatley actually had problems with his thermometer. It was very difficult at very low temperatures. So eventually there were two other graduate students. To do NMR, I had to use, the lab only had one iron core electromagnet. And two students had been waiting to use that for 3 months. So they went to Dave Lee and Bob Richardson, arguing that I should have to give up this magnet. And for that, Dave Lee and Bob Richardson agreed, and for that, they shared the Nobel Prize with me. Because if I hadn't been forced to give up that magnet, I would have never done the experiment that led to the discovery of superfluidity helium-3. So I decided I would keep my apparatus cold while the other two students found out whether their apparatus was working or not. But I decided I should do something, and so I decided this is melting pressure plotted vertically, and time is going to the right, and I would just convert liquid to solid at a very constant rate. So that's what I'm doing here. This is a capacitive measurement, so I rebalance the capacitance bridge, and it continues to cool. And then at this point that I estimated to be about 1.6 millikelvin, something looked like it was going wrong. There was a very sharp decrease in the rate of cooling. And I, of course, was very concerned about this. But I realized that I'd started, because what I thought happened was I had a mixture of liquid and solid helium-3 in the apparatus. This is, there. And so if this piston, if there had been some solid helium-3 here, the piston would have pushed against it, causing irreversible processes to occur, which would have led to heating. And so that, I assume that's what had happened here. But I started at 22 milledegrees. This is the day before Thanksgiving, 1971. So I decided that I would try this, I would cool this apparatus, the liquid helium-3, over this 4-day holiday and try this experiment again the next Monday. And so here we are. And then starting at 15 milledegrees, and then at exactly the same pressure, I saw exactly the same change in cooling, decrease in cooling rate. So I was very, very unhappy with this, of course. And I think I wrote in the lab book something bad. But ultimately I found that these features were observable, not just on cooling, but on warming, which suggested they couldn't have anything to do with heating. So here they are. We originally called this the glitch, but when it came time to publish, you have to give these scientific names, so I called this A and this E. And then here you can see B and A on warming. There was something else that was very strange, and that is that if we start, we knew this transition was about 2.6 thousandths of a degree. And if you looked at how much the pressure changed to the lowest temperature we could get in the cell, in fact, that's given by this relationship, the solid should not have had a high enough entropy to generate that large a change in pressure. Something was very strange was going on. So eventually, we found that there were two-phase transitions here. Unfortunately, I think here, yeah, you see both of them. This is the A transition, and there's this other one. We call this the glitch, and this was the glitch prime. But both of these features were, in fact, reproducible, as you see here. But the question was, were they in the liquid or the solid? So eventually, I invented an early form of MRI. In fact, this was done exactly at the time that Paul Lauterbur was developing MRI. He read my paper. He told me that later on, of course. And what I did was I applied a static magnetic field for doing the NMR, which was larger at the bottom than at the top. And then if you apply, and this is an RF coil for generating the resonance, If you apply a single frequency, you can only get a resonance where the magnetic field is at the proper value depending on the frequency. And then if you sweep this frequency upward, this resonant layer has to move downward and vice versa. So you can plot out the NMR signal of the helium-3, irrespective of whether it's liquid or solid, as a function of position inside the cell. And so this is all liquid. This little bump is because the pressure transducer itself is slightly magnetic. And so we start forming solid, and you can see these bumps growing and growing. I keep changing the gain here, 50, 100, 200 millivolts per inch. And so it isn't that the liquid signal, which is between these two solids peaks, is getting smaller. It's just these two solid peaks are getting very, very large. And so this is a temperature of about 2.8 millidegrees. But what I saw next was absolutely quite remarkable. So here now, time is increasing to the left and pressure is increasing downward. That's because I've actually turned this whole thing upside down. People always want to think of these resonance peaks as peaks, but they're valleys. And so this, if you look at so here we're going from high frequency to low frequency, and then low frequency to high frequency. So this is the mirror image of this. And you can see this liquid signal is not flat as it had been. It's rather badly distorted, which worried me. But then, in fact, we went through this V transition. This is the pressure. And suddenly the liquid signal dropped by about a factor of 2. And I didn't see this, I didn't notice this on the evening of April 17th when I took this data. But then I was looking at this day later, and I wrote in my lab book, 2:40 in the morning. This is a wonderful time to do research. No one bothers you at 2:40 in the morning. But it's more than that, there's less electrical noise in the building at 2:40 in the morning. So I wrote, have discovered the BCS transition liquid helium-3. BCS means the theory of Bardeen, Cooper, and Schrieffer that explains superconductivity. Helium-3 undergoes a very similar phase transition to a slightly different ordered state, but very similar. So then, I knew that this was correct. There was no question in my mind, and I raced around the basement of Clark Hall, the physics building, to share this exciting news with some of my compatriot graduate students. Turns out I was the only person in the basement of Clark Hall that night. In desperation, I ran up to the 6th floor to see if a theorist had fallen asleep at his desk. I was the only person in the entire physics building that night. So I couldn't stand it. At 4 in the morning, I called up my thesis advisor, Dave Lee. Before you do that, make sure you're correct. So Dave Lee called me back at 6 a.m. He wanted more, at 4 a.m. he wanted more details. And I got no sleep that night at all. Now, that was in 1972. In 1996, when I got the call from Stockholm, which went something like, hello, I said, hello, and he says, hello, hello, is this Douglas Osheroff? I said, yes, it's 2:30 in the morning. He says, I know that, but I have a matter of some importance. If you would, I am Carl Ulf Jakobsen, Secretary General of the Royal Swedish Academy of Sciences. And of course, he didn't have to say any more. I knew exactly what this phone call was about. And so he talks about, you know, the fact that they were going to release this worldwide to the press at 3 a.m. And so I said, after I hung up the phone, I said, I better go back to sleep and go to sleep tonight. And I couldn't even sit down. I kept pacing back and forth. And sure enough, at 3 a.m., the phone started ringing. And I would do these interviews, places all over the world. And then I'd hang up the phone. 10 seconds later, the phone would ring again. It would be someone else, someplace else. Eventually, I guess it was about 3 a.m., 3:30 in the morning, the Stanford News Services got hold of me. And they said, can we come up and help? And I said, what can you do? And they said, well, for one thing, we can manage your phone. I said, come on up. They said they would be up at 4 a.m. So I did several more of these interviews. The doorbell rings at 4 a.m. I told whoever it was, I said, I'll be right back, I've just got to open the door. I ran up, opened the door. It wasn't Stanford News Services, it was a photographer taking pictures of me in my pajamas. Anyway, so that's how that goes. So this is, I'm getting ahead of myself. But eventually Dave Lee suggested that we have two phase transitions. It was very clear that the lower temperature transitions was in the liquid, but we thought that the higher temperature transition was probably in the solid. So Dave says, get rid of this magnetic field gradient, and let's see if the solid NMR signal the frequency is temperature dependent. What we found was exactly the opposite. The liquid signal was temperature dependent. And so we found, in fact, that clearly the liquid, these were both transitions in liquid helium-3, but this had never been predicted. In fact, we took data in many different magnetic fields, and if we plotted the liquid frequency squared minus the solid frequency squared, all the data collapsed on a single line. So we didn't understand this, but we submitted this for publication. It was rejected. Not once, but twice. The reviewer felt that we didn't understand how to do nuclear magnetic resonance. This is such a weird result, but it was really, we sent a preprint of this paper to Tony Leggett, who was I guess, associate professor at the University of Sussex in England. Tony started thinking about this, and Bob Richardson and I agreed that it took Tony Leggett less than 3 weeks to figure out what the hell it was that we had discovered. And so Tony Leggett actually won the Nobel Prize. But let me get back to strategies. First of all, utilize new technologies to view nature from a new perspective or in a different realm. Number 2, don't give up when things are going badly. Very important. Failure may be an invitation to try something new. So when the students took away my magnet that allowed me to do this experiment that wasn't going very well, I tried something different. Immediately discovered something that ultimately won a Nobel Prize. 3, spend a little bit of time doing something different. Curiosity-driven research is fun and it can be rewarding. So this experiment that led to the discovery was not something that Dave Lee had told me to do. It was something that I was doing just to bide my time until I could get the magnet back. And this is a really important one. My wife, as you understand, is Chinese, and she wanted me to learn. Cornell was offering a course in conversational Chinese my last year of graduate study. So my wife thought it would be fun for me to take that course. How many Chinese? Probably you can't understand my Chinese anyway. Xiaosewala. Anyway, I didn't take the course, but I think if I did, anyone that knows Chinese would know from what I just said that I didn't take the course. But if I had taken the course, my guess is that at the time that they took the magnet away from me, I would have been so far behind in my Chinese, I would not have done the experiment that led to discovery. So I think this is really one of the very important things. When you're doing research, if you're a graduate student, and in my case, I suppose I was commanding something, maybe $100,000 worth of equipment or something like that. You don't have that forever. This is a rare opportunity. Don't waste it. Avoid too many commitments. And then finally, back off from what you're doing occasionally to get a better perspective on the task at hand. I didn't tell you this, but a squirrel gave his life to allow me to make this discovery. What happened was the squirrel had managed to short out the electric power coming into Cornell University, and that caused one of my pumps to leak air backwards, and so I had to warm up the cryostat. And it was only because of that I had time to think about how I could differentiate the liquid NMR signal from the solid. That's how I invented MRI. If you continue to bang your head against a wall, you're very unlikely to come up with any good ideas. Okay, so we're almost done now. This is Dave Lee, my thesis advisor. This is yours truly, and Bob Richardson. You always take these pictures, and I think I had to get permission from the photographer to even use this in a PowerPoint presentation. If you look very carefully, Dave Lee and Bob Richardson have been very careful to orient Nobel's image so that it's correct and mine is not. They didn't take the prize away from me, however. And that was 1996, and so 4 + 3, 7 years later, Tony Leggett is getting his own Nobel Prize for having basically worked out the spin dynamics of these remarkable ordered states. And so here now I put up, again, this Pomeranchuk cell, my Pomeranchuk cell, and I put the names of people, I would say, that contributed either insights or technologies that were essential for me to make this discovery. Bardeen, Cooper, and Schrieffer for their theory that explained superconductivity, and then was used by Phil Anderson to predict superfluidity in helium-3 in 1959. Pomeranchuk for his prediction of this, or suggestion of this wonderful refrigeration technology. Ed Hamel for having introduced the world to liquid helium-3. Wheatley and Landau for their understanding of the normal state properties of liquid helium-3 at low temperatures. Bloch and Purcell for their invention of NMR. I mean, it was important in every aspect of this work. And Edwards and Hall for their development of the invention of the helium-3, helium-4 dilution refrigerator. So without any one of those, I would say I would not have made this discovery. So let me end by putting my glasses back on. Advances in science are seldom made by individuals alone. They result from the progress, excuse me, They result from the progress of the scientific community, asking questions, developing new technologies to answer those questions, and sharing their results and their ideas with others. To have rapid progress, one must support scientific research broadly and encourage scientists to interact with one another and to spend a bit of their time satisfying their own curiosities. This is how advances in science are made. Thank you very much. I probably went over, when I'm enjoying a talk, it goes slow. You're a good audience. I would be happy to answer a few questions if people have any.
Dr. Osheroff, we are honored to have you here at UTEP in El Paso. This is one of the most interesting and challenging lectures I've heard in the last 30 years here. Now, you have given us some insights into your scientific career, starting with your high school science club, but this pocket biography here says that at the age of 6 you took apart your toys to get the electric motors for them, which indicates that this intellectual and scientific curiosity must have been started much earlier than that. Can you give us any idea, if you can recall, if there was any one person, one event that was...
Yeah, thank you. That's an excellent question. I think the answer is that it was my father. I distinctly remember when I was very young in the basement, my father had me wind a coil of wire around a nail, and then we connected the wire to a battery, and suddenly the nail became a magnet. And it was just absolute magic as far as I was concerned. And I think that really started things. When I was 8 years old, I think I was 8, maybe it was 6 anyway, I was given an electric train for Christmas. And my father would take a nap every afternoon from 1 to 2. And during that hour, I took the locomotive apart to get the electric motor out. And my parents could have said, "You destructive devil, you," and sent me to bed without my supper or something. But I think particularly my father was fascinated with my fascination. And so from time to time, he would give me things to play with, usually thinking that they were benign. But in fact, I think on at least a few occasions, I came close to killing myself or other members of the family. So I think it was really my father. And I think my father was actually a graduate student in chemistry when the Great Depression struck. And, well, I guess it was probably, anyway, it was during the Great Depression that he was in the middle of a PhD, and I think he'd gotten his master's degree already. And his father, who was a medical doctor, said, "If you go into chemistry, you may never have a job." but if you go into medicine, you will always have a job. And so my father changed and went to medical school, and I think in some ways he regretted not having gone into science himself. So I think I benefited from what was for him a happy adventure. Any other questions? Yes?
I have a question, but maybe I should go to the microphone.
Go to the microphone.
You know, it's so interesting seeing you with the theories and the contributors to BCS theory, for example, and your own work and so on, leading to the prize. And my question is why is it that we've had such trouble with the higher temperature superconductors with all this background? Do you have any thoughts on that? I don't think we really understand them.
These materials are actually remarkably complicated, and I think, you know, the BCS theory works very nicely for simple materials where you have a very clear Fermi surface, which probably doesn't mean anything to 3/4 of the audience right now, and in particular you form Cooper pairs where you have one electron has it spin up and one electron has it spin down. That's really the sort of system that the BCS theory was really designed to create it, to explain. But these now we have L equals 1 and L equals 2. L is the orbital angular momentum of the Cooper pair that forms, and there's just a lot of extra degrees of freedom. I suppose that helium-3 was the first example of a BCS state where there were additional degrees of freedom, that is the nuclear spins themselves and the orbital angular momentum. And so it was, in some sense, I think, maybe a classroom for physicists to understand what was going to happen eventually when they discovered all these high-temperature superconductors. Thank you very much. Interesting question. Yes?
I am very thankful to be here tonight. I am not a scientist, but at El Paso High School we had a wonderful teacher for chemistry. And
Me too.
I did not want to take biology and have to dissect a cat's face. But anyway, I came from El Paso High School here when it was a college of mines. And it was a wonderful school then of about 3 or 4 buildings. No, I think it had more. Anyway, a few more. But the registrar put me, each person had a talk with the registrar to enroll. And he put me in English and history and this and that. And then he put me in an engineering chemistry class. And I said, why are you doing that? I'm not going to major in engineering. And he said, it will give you 1 more hour. And so, well, I made a C. I think because the professor was a neighbor of ours. His name was Ball, B-A-L-L. And I had a terrible crush on what he said. But his son. But anyway, I am thankful that I had that chemistry course because I could understand just a little bit of what you say.
It's very difficult to explain a scientific subject without using some science. I apologize. But I very much enjoyed your criticism. Thank you.
Let me thank you very, very much for spending time with us today. A small token of our appreciation. And let me thank all of you for coming. And there's an informal reception just outside the auditorium, and I hope you'll join us, and there'll be an opportunity for some direct interactions.
Thank you. I would just like to say one more thing. 今天天气好极了。